Okay, hi guys. I know that you were supposed to have a guest lecture today. He was unfortunately unable to finish his lecture for today, so it should be ready by Wednesday. He's now asking me if he can teach it live during Wednesday class, so that may happen. So there's not many of you guys, so maybe a lot of people didn't get the email that I will be teaching today. People are joining now. Okay, so as I was saying, maybe some people didn't get the message because we were supposed to have a guest lecture today. But as I said, that will be on Wednesday's class now. So I'll send out another email. He's just asking me if he can teach it live instead of pre-recording it. So if that's the case, we'll all meet in this regular classroom like normal, except I will not be teaching. It will be Siddharth from the World Bank. Okay. So any questions before we begin? Just a reminder that you guys have an assignment due on the 21st, so in 2 days, as well as your referee report on the 29th. So is there any questions on either of those two assignments before we get going? Okay, great. Just a reminder, I know your assignment is due in 2 days, 19th or 3 days, so I'm sure you have started already, but make sure that you know that you can work in groups of 2 if you want to. You can either work individually or in groups of 2. So if you do work in a group of 2, just send one email for the group of 2 people and include both names, and that will be good. Okay, so just make an effort to come to class on Wednesday because I do believe our guest lecturer will be teaching live now. So it'd be nice if there was more than 10 of us. Okay, so I'm gonna share my screen. Okay, so we left off on Wednesday talking about diff and diff. So I'm sure you guys will remember this slide. So basically what we did here was show the difference in difference method. So remember that if you're looking at these two lines, this shows the employment trend over time. So see how time is on the x-axis and our y, or outcome variable, is on the y-axis. So here we have employment rate, and we're looking between the comparison group who does not receive treatment and the treatment group who obviously does receive treatment. Okay, so these are their time trends of their outcome. You can see in year 0, they receive treatment, so they're using this period as the before, and year 1 as after. So they are basically, to do a diff and diff, I'm sure you guys will remember that we are basically combining a before and after with a enrolled versus not enrolled comparison. So when we say a before and after comparison, we're really only looking at the treatment group. So we look at the outcome of the treatment group after they receive treatment minus before. So it's just a difference in means within the treatment group after minus before. It's very simple. And then the enrolled versus not enrolled comparison is what we generally were talking about in chapter 2. So comparing it, the treatment group outcome to the comparison group outcome. So in this table, it would be just B and D, right? We're only looking at the post period. So after treatment is given, we're looking at post period, the difference in outcomes between the treatment group and the control group. Okay, so that is our enrolled versus not enrolled comparison. And recall that the problems with there were different problems associated with the before and after comparison, as well as the enrolled and non-enrolled. So with the before and after comparison, the main problem was that other things change over time. So we call that time variant bias, because we might not only be capturing the effect of the treatment, maybe we're also capturing some other effect that changes over time, such as another policy, improvement in the economy, or whatever, different environmental factors. So time variant bias often affects before and after comparisons, whereas for enrolled versus non-enrolled, we're typically concerned about selection bias. What makes a group more likely to take up treatment than the control group? Well, there's probably some sort of characteristics that vary between the two groups. So the difference in differences method, as you guys recall, is combining the before and after comparison with the enrolled versus not enrolled. So that's why you see how we have time trends for the group that receives treatment, and then also a time trend for the group that does not receive treatment. So in that way, we could take a before and after comparison for both the treatment and control group. So that would be our first differences. And then afterwards, take the difference of those two numbers, and that will be our second difference. So that's why it's called difference in differences. It's pretty logical. So for example here, to conduct our before and after analysis for our treatment group, we would want to go the outcome for the treatment group in the after period. So you can see year equals 1. And so we see that that's B equals 0.74. So that's like the outcome employment rate in the after period. And then we subtract the before period, which is in year 0, and that's A equals 0.60. So the employment rate in the pre-treatment period is 0.60. So if we subtract those two numbers, that's our before and after comparison for our treatment group. And then we can do the same thing for the control group. So you would see, you go D minus C, 0.81 minus 0.78. And then you finally subtract those two differences. So we always want to go treatment minus control. So whatever the difference we get for the treatment group, we'll subtract the difference for the control group from that. So it would be B minus A minus D minus C. Okay, so if you guys are confused by what I just said, go back to the last slides and the recordings. We went through examples on the whiteboard, so that should be more clear if you weren't too sure. Okay, so then you can also do the same effect analysis using enrolled versus not enrolled, except in year 1 minus year 0. So the first time we use the before minus, or the after minus before, right? So we did the before and after comparison, and then we compared the treatment group to the control group. Well, we'll get the same results actually if we instead do enrolled versus not enrolled between the two different time periods, okay? So we could go the treatment group minus control group outcome in year 1, so it would be B minus C, and then subtract off the difference in the pre-treatment period, year 0, so A minus C, and you'll get the same effect size. Okay, is there any questions on this graph here? Okay, great. So this just explains what we just talked about, so I won't cover it again. Oh, okay, so another thing to notice about this graph is this E here, right? We didn't mention the E before. Well, if you recall, the reason why we have a comparison group is to basically measure trends in the time trends for our treatment group. Because we can't isolate the time trends for our treatment group because they're also receiving a treatment effect. So to be able to isolate the time trends from the treatment effect, we use a comparison group, and we say, well, if these two groups experience the same environmental conditions and their outcome trends in the same way before treatment, then we can assume the same would be true after treatment, except the only difference is that the treatment group receives some sort of treatment effect. So you can see how this is the perfect example because our two graphs or two lines perfectly match each other. So you can see that they're clearly subject to the same environmental conditions. And you see this line for the comparison group, how it goes up and up. Well, we're going to estimate that that would be the same for our treatment group in the absence of treatment. So that's where this line E is here. So this line here is basically our estimated counterfactual group for our treatment. Sorry, our counterfactual for our treatment group. So that's really important. And that will give us our effect size, right? So what we actually want to estimate here, the estimated impact, is B minus E, because E is what we gain. This is our counterfactual that we estimate using our comparison group. Okay, so technically our comparison group isn't our counterfactual. This line here, the E, is our counterfactual, and that's because we're only using the comparison group to estimate time trends. So you can see that these two lines aren't on the same level. So we're just using this to show where the treatment group would go in the absence of treatment. So that's the main purpose of a control group in difference and differences. Is there any questions on that? Okay, great. So yeah, this would be the math here. It's pretty simple. If you were doing the before versus after, you can just work it through later. Okay. So this just highlights the difference in differences method, which we basically just talked about, so I'm not going to restate it. And then I say that we could also compute the difference in differences the other way around by first calculating the difference in outcome between the treatment and comparison group in the after situation. So that's the enrolled versus not enrolled in period t equals 1 minus the effect of enrolled versus not enrolled in period t equals 0. And so either way, you get the same effect because you can see how whichever method you choose to actually calculate it, you're still using both the enrolled and not enrolled and the before and after. So it's still a combination of the two and you'll get the same results. But make sure that you're always going treatment minus control, right? Because we care about the treatment effect, so you want to put the treated group first, just to interpretation's sake. Okay, so this highlights it again. So yeah, this is just showing the different two ways you can do it. So you can see for a treated group, after is B, before is A, so the difference is B minus A, and then the comparison group is C minus C, so their before and after comparison is Z minus C. Or you can do it the other way and go treatment minus comparison group, so B minus C, and then the pre-treatment period is A minus C, and so you subtract and you see you get the same. Okay. Okay, so we've talked a lot about how we're using the control group to estimate the time trends. So the most important assumption, basically the only assumption of difference and differences, is known as common trends. Okay, so this is what you need for your difference and differences to be valid and to assure that you have causal inference. So it's requiring that in the absence of treatment, the difference between the treatment and control groups is constant over time. So that's basically saying that these two groups, they don't have to look identical to begin with, so they don't have to be on the very same line. However, if this treatment effect didn't exist, the trends between the two groups shouldn't change. You saw in this picture before they had really great common trends because you can see how they're basically parallel the whole way through. And that's showing that it gives us reason to believe that they would be the same after treatment, except that the only difference is one is treated now. Okay, so that's the real reason why it's super important. If we don't have good common trends, then we can't say that we're correctly estimating the counterfactual. Okay, so this is called common trends, also parallel trends. And what we need is that, common trends means that before treatment, we're only thinking about before treatment right now when we think about common trends, is that the treatment group and the control group, their outcome variable trends very similarly. Okay, so we must assume that no such time-varying differences exist between treatment and comparison groups. Although there isn't really a statistical test for this assumption, visual inspection can be useful. Okay. So, since, as we know, we can never observe both potential outcomes for any individual or group, so that would be, I don't know if you can see that, Y0i and Y1i, right? So this is the outcome if you do not receive treatment and the outcome if you do for individual I. We must assume then, in the absence of the program, the outcome in the treatment group would have moved in the same motion or in tandem, which just means parallel, with the outcome in the comparison group. Okay, so I'm sure you guys have learned about common trends in other econometrics classes. So yeah, it should be pretty straightforward. So basically, what if our two groups, if they're pre-trends, we call them, because they're the trends of our outcome before treatment, so pre-trend. If they are not the same, then we will have an invalid estimate and it will be biased, because I'll show you some examples. Okay. So we're looking at pre-trends right now on the Spanish keyboard. Pre-trends, common trends. Okay, so when we're looking at common trends, recall that we want our treatment group and comparison group to be affected similarly before treatment. So this is our outcome, Y, and this is time. Beautiful. Okay. Okay, so that is, say t equals 0, so that's the treatment. That's when they receive treatment at t equals 0. So let's look at the treatment group. Let's say this is the treatment group. And this is the control group. Okay, so then if we're using our diff and diff, we're using our control groups, or I'll label this. Okay. So we're using our control group to estimate the trend of the treatment group if they didn't receive policy or if they didn't receive treatment. So basically what we're going to do is take this post period and mirror the line that they have. Okay, so let's say Okay, so you can see how I'm just matching the control trend line in outcomes to the treatment trend line, starting from where it left off at the treatment effect. Okay, so this right here, as I mentioned before, is, what is it? Who can tell me? Who knows the answer? What is this black dotted line? The control trend, projected trend. Close. So the control trend is the line on the bottom here. So it's actually the counterfactual. Not quite the effect. Okay, so just the line itself is the counterfactual trend. Because look, this line down here is our control line. So this would be the trend line for our control group. This is the trend line for our treatment group. So this line right here, we don't actually observe it, but we're saying this line is what the treatment group would observe if they don't receive policy or if they don't receive a treatment. So yeah, I guess this is the potential outcome of the treatment group that we cannot see. So we have to estimate it. Okay, so not observe. Estimate. And how do we estimate it? Using the control group. Okay, so the counterfactual, we don't actually observe in reality. We have to estimate it based on what we observe of the control trend, right? Because we know that our control group does not receive treatment, our treatment group does. So we can't actually measure the time effect in the treatment group because then it will be mixed in with the true treatment effect. So we can't use the treatment group. So we use the control group to measure the counterfactual of the treatment group by saying that the counterfactual would be the same trend line as the control group except for the treatment group, right? So you can see how we just mirrored this line here after the treatment period. So that's our counterfactual that we estimate. And you can see why it's so important that we have valid pre-trends or common trends based on, oh, that's cool. Yeah. So you can see how it's important that we have valid common trends, or else we won't accurately estimate the counterfactual group, and that would bias our estimates. They could either be overstated or understated, depending on how the trend lines are different. Okay, is there any questions here about the difference between the control group and the counterfactual in this case, because they're not exactly the same? And then here, just so you guys have it in mind, don't do that. This difference here, okay, so say this is t equals 1 here. This is our after period down here. What is the difference between the t line and the counterfactual? That is our treatment effect of interest. That's our effect size. Okay, so you can see here the TI1 is our after period. And so we're using the control group to estimate the counterfactual for the treatment group. And the difference between those two lines is the actual effect size that we're estimating. Okay? If that is clear, then I'm going to erase this picture and show you guys some different trend lines and see what you think. Okay, let's go then. Giddy up, cowboy. Here. Okay, so two different ones. So this is our y as before, time and that's our treatment period. So we'll call that, let's just always say t equals 0 at time of treatment. That's easiest. Okay, so -4 -1. Okay, so let's say, what should we say? Okay, so if we find this, so flat line, let's see, positive treatment effect for the treatment group. We're saying we only have 2 periods of pre-treatment, right? And then this is this. Do you guys think that is a valid counterfactual that we would estimate using those trends? Yeah, not really. I agree with Nicholas because you can see we need parallel trends, right? So although the trends look parallel in the post period, that's not what matters for validity. We need parallel trends in the pre-treatment period, right? So this is pre-treatment. And that's post-treatment. So parallel trends, even though they look good here, that's not what we care about at all. That's where we expect to see the treatment effect. What we need for validity and to have unbiased estimates is to have parallel trends here. And to me, they're not really matching because this is very horizontal, whereas this is increasing. So that wouldn't be a good example. Okay. Let me do another one. Okay, so say it's hard. I can't think this creatively. Okay, oh I know. Okay, so say that's our treatment group and this is our control group. Do you guys think this is a valid counterfactual or what? Well, control group to produce our estimated counterfactual. What are the opinions here? This one's definitely harder. It can depend according to the effect that is wished to estimate. If it's short-term effect, it might work. Okay, so I would also agree it does depend. To me, it doesn't depend on what the effect we wish to observe, whether it's short-term or long-term, but rather it's only, I think it matters because, for example, here, we observe 4 pre-treatment periods of the control group, and we only observe 2 of the treatment group. So it's going to make a difference whether we think that, oops, someone's saying how long we want to be back in time. Yeah, so the more time we have backwards, it's better, because if the true line is like this, if our trend line is linear, then we won't have a good estimate, right? Because this is just looking like this. So then that wouldn't be good, because we wouldn't have a very good estimate of the treatment effect. Okay, so it could also be like this though, because we don't have these 2 years of data. If it was like this, if it looked the same, then we would have a good counterfactual, right? So that's bad, that's good. If we don't have this data, it's really hard to say which is which. So in this case, obviously the more data you have for pre-treatment, the better you can argue you have a valid counterfactual by similar pre-trends. If you showed a paper like this where you just show the red lines, a lot of people would say, well, I mean, for 1 or 2 periods they look the same, but is that enough? So, I mean, it's less clear in that case, because you don't know whether the pre-trend line for the treatment group is going linearly, or if it's matching the same cyclical pattern as the control group. So that case is really unclear. But as an author, you definitely want to try and argue that this is good enough if that's all the data you have, right? So it's all about proving your methodology is strong and trying to kind of test it and see whether it passes these tests that kind of check your assumptions. So this visual trend is definitely one check. You can do a graph like this. That's the most common way for authors to show that they have valid kind of counterfactuals. Okay. Susanna asked, how many periods before treatment are enough? That's really subjective, I believe. So, I mean, it depends. Definitely at least 2 periods, because if you only have 1 data point before, it's hard to say. It's not a trend, it's just 1 point before. So definitely authors are now trying to go 5 to 10 periods. So I definitely try to go somewhere in there. We need parallel trends. Yeah, parallel trends, exactly. So this is kind of showing whether trends are parallel or not. And if you're doing a difference in difference paper, it's important to show a graph like this. So y is your outcome variable, and show 2 trend lines, one for the treatment group and one for the control group. And most importantly, we care about the pre-treatment period. So the more periods before treatment you have, the better, because it can kind of check the trend lines and see whether the 2 groups are subject to similar environmental conditions. Okay, so I'm going to clear this. Okay, this is a picture similar to what we were just talking about, but this is an example with bad trend lines. Okay, so you can see how, I mean, it's hard to say, right? Because if you only had 1 year of data, it would look like a great trend line. But when you go further back, you can see, oh, maybe this is linear, whereas this line is more cyclical. So if we had an actual cyclical trend for the comparison group, it's hard to say whether we could accurately show the true counterfactual, what the treatment group would observe for their outcome variable in the absence of treatment, right? So that's why pre-trends are super, super important, because we're relying on the control group to create a counterfactual that captures time trends. So to show that they exhibit similar time trends is very important in that sense. Okay, so in terms of expectations, the assumption underlying the diff and diff is that in the absence of the program, individual outcome at time t, individual i's outcome at time t is given by the expected value of yi given di equals 0 and t equals t, so this is the control group at time t. It's just a function of gamma I and lambda t. So that's saying that for the control group, their outcomes are only a function of a fixed effect for the individual level, so that's gamma I, and lambda t, so that's a time fixed effect. So for the control group, their outcomes are only captured by an individual fixed effect and a time fixed effect. So that's really important for the diff and diff validity, because remember that the difference in differences is comparing between two groups over time. So we need to assume that within one group, just doing a before and after comparison will eliminate selection bias. And then comparing between the two groups, the control group can basically eliminate the time trends. Okay, so as I said, the implicit identifying assumptions here is that selection bias relates to fixed characteristics of the individual, gamma I. This implies that the magnitude of the selection bias isn't changing over time. So that's really important, because if we're thinking of comparing within one group, so the treatment group, their outcomes after treatment minus their outcomes before, we need to assume that when we do that, we're eliminating all selection bias. So their characteristics are the same after as they were before. If not, we can't really rely on a difference in differences. So that's the underlying assumption to a difference in difference. Also, that the time trend, lambda t, is the same for the treatment and control group. So together, these are known as the common trend assumption. So that's basically the principles of difference in differences, that we remember that it's a combination of the before and after and the enrolled and not enrolled. So they can efficiently, combining those two methods, can eliminate individual characteristics and time biases, so that we're left with only a treatment effect. Whew. Okay, so in the absence of the program, individual I, sorry, I said is, it's I apostrophe S, person I's outcome for group I at time t is the expected value of y0i. Remember, that's our outcome when you do not receive treatment. For the group di equals 0, recall that that's our control group, right? So the dummy variable di, we always say, is our dummy variable for treatment. So when di equals 1, the group receives treatment, and when di equals 0, the group is the control, so no treatment. And then we're saying time equals t. Okay, so the expected value for this group, as we just mentioned in the assumptions in the previous slide, is equal to gamma I plus lambda t. So the outcome is a function of individual fixed effects and time fixed effects. That's it. Okay, so the two potential outcomes for the comparison group then are using this term, right? We're using this term right here. So the expected value of y0i for the control group, di equals 0, in time equals 0, t equals 0. So that would be pre-policy. We're calling that pre-treatment period. And so in terms of the second part of the equation here, right, we're just basically carrying over. So that's equal to the expected value of the individual I's fixed effects, given that they're in the control group, plus the time fixed effect for that period, t equals 0. So that's why it's lambda 0 because we're looking pre-policy, which is t equals 0. And then the same for the period 1 outcome for the comparison group. They're still not treated in the post period, so they're remaining as y0i. They're still the control group, so di equals 0, but now we're looking at the post period, so t equals 1. So that's just the same, so you can see how it's still a function of the individual characteristics, so the expected value of gamma I given you're in the control group, but now there's a different time trend, right? So there's the lambda 1. Okay, so the only difference for the control group between the pre-period and the post-period is the time effect. Is there a question right now about these equations and why we're only considering time and individual fixed effects for the control group? Okay. So we're using the comparison group to estimate the time trends, as I mentioned before. So remember that we're just looking at the difference in outcomes for the control group in period 1 minus period 0. So post-treatment minus pre-treatment. So that's just what we saw before, right? So we have y0i for the control group, di equals 0, and time equals 1, post minus pre for the control group. And so that's just equal to a function of their individual fixed effects plus the time trends, right? So you can see how for period 1, t equals 1, we have the individual i's time, or the individual i's fixed effect plus the time trend for period 1 minus the before period. So we have the individual fixed effect plus the time trend, so lambda 0. So when we subtract those two, this is the after minus before, or the before after comparison for the control group. All we're left with is the time trend, right? Because you can see how the individual fixed effects, they're constant over time. There's no t here, right? It's only gamma I. That means it's constant over time. It only varies across groups. Since we're looking at the same group, this is the same value, so they just cross out. They are canceled. And so we're only left with the time trend. Okay, is there any questions there? Okay, great. Now let delta represent the true causal impact of the policy, right? So that's our causal impact. So delta will be the difference in treatment outcomes for the treatment group when they receive treatment minus when they don't receive treatment. So these are like the two potential outcomes for the treatment group. So the expected value of y1i given di equals 1, so you're in the treatment group, and time equals t, minus the second potential outcome when you don't receive treatment for the treatment group, and time equals t, right? So it's in the same moment of time for the same group with both potential outcomes. So remember, this is the counterfactual problem. We don't actually observe this. We need to estimate for it. Okay, so yeah, notice how the true causal estimate or impact is always the average treatment effect on the treated population. This means there is no selection bias here because we are comparing the outcome of receiving the program against the outcome of not receiving the program for the same treated population, so no selection bias. Also note that this causal impact doesn't depend on the time period or characteristics of individual I. Okay, so we looked at the potential outcomes for the control group. Now it's something similar for the treatment group. The only difference is that the treatment group in period 1, in addition to their individual fixed effects and time fixed effects, they're also going to have a treatment effect, right? Because they're the treatment group. So in period 1, in the post period, they receive treatment. So you can see here, you can see here that the pre-treatment outcome for the treatment group is the expected value of y0i given di equals 1, so you're in the treatment group, and t equals 0. That's pre-period. That's equal to the individual fixed effect for the treatment group plus the time trend for period 0. And then the post period is the same, right? We have the outcome of being treated, so y1i for the treatment group in time t equals 1. That's still, we have the same individual characteristics, but now we have a delta on top, so our treatment effect and the time trend. Okay, so basically differences in outcomes pre-treatment versus post-treatment. So if we just did before and after for the treatment group, can't be attributed to the program treatment effect because we also have the time trend here, right? So this is our before and after bias. When we look at the treatment group, you can see how if we just subtracted the outcomes of after minus before, we would capture the treatment effect, but we'd also have a time effect that we aren't controlling for. Okay. Before we get there, I'm just going to take the 10-minute break so you guys can think about it, chill, look at some memes. So I will see you at 7:01, okay? Ah, I changed my keyword for an email. Okay, that should be good. Okay, let's start again. Last path. So, yeah, as I was just talking about, we were looking at the potential outcomes for both the treatment group and the control group. So remember that the potential outcomes, well, for the control group, are only made up of an individual fixed effect, which is constant over time, plus a time fixed effect for each time period. So we're only looking at 2 periods in this model. So it's just before and after, very simple. And the same thing for the treatment group, except that the after period is composed of not only an individual fixed effect and a time fixed effect, but also the treatment effect of interest, right? Because now we also have not only the individual characteristics and the time characteristics of an individual eye's outcome, we also have the fact that the treatment group is receiving treatment. So that's what we're trying to isolate for. And yeah. Okay, so what we're going to do is combine a before and after comparison with an enrolled versus not enrolled. Remember what we did in our graph maybe at the beginning of class, but before then we just said B minus A is B minus B. So that was pretty simplistic looking at a picture. This time we're just going to think about it in terms of expectations. So this is a bit more mathematical, but don't let the letters and numbers scare you. It's actually very simple to look at, so we'll break it down line by line. Okay, so if we were to do a before and after comparison for the treatment group, this is what it would look like. So for period 1, we have the expected value of y1i, so the outcome for the treatment group if they receive treatment. So di equals 1, treatment group, t equals 1, that's our post period, minus the expected value of the outcome if they hadn't received treatment for the treatment group in period t equals 0, so before. So after minus before for the treatment group. And that's equal to, for the after period, the individual expected value of individual fixed effects. Wait, that should say 1. For di equals 1, 1, 1, 1. If you're making note, that does say 1. For the treatment group, di equals 1, plus delta plus lambda 1. So this is the treatment or individual fixed effects for di equals 1. So that's my mistake in the note. Minus the expected value of individual fixed effects, gamma I, for the treatment group, plus a time trend for the period 1 outcome, right? So this is before and after. So our after period is composed of individual fixed effects, a time fixed effect, and the treatment effect. The before is just the individual fixed effects and the time fixed effect. So if you see when we do a before and after comparison, we're left with, we subtract these two. The only thing that cancels out is our individual fixed effects, right? Those are the only things that are the same. This should be di equals 1. So those two cancel. We're left with our treatment effect and a time trend. So lambda 1 minus lambda 0. That's our time trend. So alternatively, we could calculate an enrolled and non-enrolled analysis. We would obtain this. So the expected value for y1i, right? y1i is the treatment outcome if you receive treatment. For the treatment group, di equals 1. In time, t equals 1. So that's after. Minus the non-enrolled group, right? So we're comparing between enrolled and non-enrolled this time. So that's the y0i outcome if you don't receive treatment, given that you're in the control group and t equals 1. So you can see here the time period is the same. They're both in the post period, so the treatment effect has already been implemented to the treatment group and the control group hasn't received it. So then if we take the differences, we'll be left with the expected value of gamma I for the treatment group, di equals 1, plus the treatment effect, plus the time trend for period 1, lambda 1, minus the control group. So they're going to have a different set of individual characteristics, right? The expected value of gamma I, given you're in the control group, plus lambda 1. So that's your time effect. So then when we do an enrolled versus not enrolled, you can see how we're left with the treatment effect plus the selection bias term, and that's the difference in the expected values of individual characteristics. Okay, so I'm showing you this to see how our biases are created between the enrolled and non-enrolled and the before and after. So there are two different biases, right? So how are we going to use the diff and diff to eliminate both? Let's see. Any questions here on any of the terminology or why things cancel? I think the main thing to remember is that we're saying since gamma is only subscripted by I, we're saying it varies across individuals or varies across groups, but is constant over time. So that's why we can subtract between one group the individual characteristic term. Okay, please don't be shy if you have any other questions. I don't know if you guys have seen expectations like this before. So if it's not clear, when we're thinking in terms of regression analysis, the expected value of yi will just be the mean outcome for your treatment group, right? So it's really simple. This is just the mean. Think of it like that. Okay. So for the difference in differences then, we're comparing our before and after comparison with the enrolled and non-enrolled. And that's how we obtain our causal estimation. So here we're doing before and after for the treatment group minus the before and after for the control group, right? You can see how we have, always look at the conditions first to make sense of it. So you have CI equals 1, so we have treatment group minus treatment group, after minus before, right? So T equals 1, that means we're after post-treatment, and T equals 0 is pre-treatment. So we're clearly doing a before and after comparison. So the after minus before, then minus the after minus before for the control group, DI equals 0. Okay, so that should be super clear. We're just, what we said in the graph before, the two before and after comparisons, we're combining treatment group minus control group after minus before. Okay. So then for the treatment group, we're left with what we calculated in the previous slide. So that's the expected value of gamma I, so the individual fixed effects for the treatment group, plus the treatment effect, delta, plus the time trend, lambda 1. So that's our post period. Post period, preposterous. Yeah, and then you subtract the pre-period, so the expected value of gamma I for the treatment group, so it's the same, right? These two are identical, plus a different term. So we have the time trend as lambda 0. Okay, now we want to subtract the difference in the post minus pre periods for the control group. So we have minus, all in brackets, see there's parentheses, the expected value of gamma I given you're in the control group. So this is the individual fixed effects for the control group, plus, plus lambda I, and then minus, there should be a minus between lambda I and E, because it should look the same as the top line, right? So minus the expected value of gamma I given DI equals 0, so given you're in the control group, plus the period 0 time trend. So when you subtract these two, you can see how can you guys see my mouse when I wiggle it? I hope so. Or else I'm waving it around for nothing. So I can cross out all the individual characteristic trends between within each group. So for the treatment group, these get crossed out. Same for the control group. So we're left with no more selection bias terms, no more differences in characteristics by individual. And then you can see how we can eliminate both the time trends because, I mean, just look at it. You have a positive time trend. That should be the same for each group. So that's the lambda 1 for the treatment group minus here the lambda 1 for the control group. So those two go away. And the same for lambda 0. You have a minus here, a negative, and that should be an extra minus here. So those two cancel. And all you're left with is the treatment effect, delta. Okay? So notice that this is really critical that we're able to cancel out the selection bias term, so the gamma i's, and we're able to cross out the lambdas, right? So lambda 0 between the two groups. And the lambdas are telling us the time trend, so that's why to be able to cancel them out, we need them to be the same. So that's why we need the control group to show the same time trends as the treatment group pre-treatment. So that's where the common trends come from. Any questions? Okay, so just the basis of that is that each group, basically their baseline outcome is a function of individual characteristics and time effects. So the only difference between the two groups is that they have different individual characteristics, but they should have the same time trends, right? And the individual characteristics stay constant over time. And then the main difference that we care about between the treatment group and the control group is obviously the delta, the treatment effect. So that's what we're isolating for. Okay, if that is super clear, I will move on. Since no one's asking anything and people are leaving. Probably boring, I'm sorry. Okay. So yeah, this is how the difference in differences recovers the true impact of the program, as long as the common trends assumption isn't violated. Okay, so now looking at the regression format, which is probably what you guys care about if you're ever doing an analysis using whichever program, Stata or R. So the formal model of the difference in differences can be characterized as the following. So it'll be our dependent variable y for individual or group I at time t is a function of alpha plus beta di, our treatment dummy. So di equals 1 if you're in the treatment group, plus rho times post times with subscript t. So this is only a time variation dummy. So for example, post equals 1 if time equals 1. So you're in the post period. And finally, delta is the treatment effect of interest, which is the interaction term between these two variables, di and post. Okay, so what beta is basically going to do is capture the selection bias variation, right? Because it's the difference in the gamma I for the treatment group and the gamma I for the control group. So that's selection bias, so we don't really care about interpreting this variable, plus rho times post, so that's the variation between post period and pre-period, so that's capturing our time trend. And then finally, the interaction between the two is what we care about. Okay. And just be careful of the subscripts. So notice here, our treatment dummy is only subscripted by I, because you're either in the treatment group or you're not treated for the whole period. and then T is the time period, right? So that's going to tell us, okay, the treatment group is treated past this period. And so the combination of the two is what we're actually interested in. Okay. So in the case of difference in differences, treatment doesn't always have to be a dummy variable. It could also be some intensity of treatment. So maybe your variable is continuous. So it could be the same kind of methodology, except that your treatment variable is intensity. So the most treated would be 1, for example, and the least treated would be 0. And it can take any value between 0 and 1. That would be an example of a continuous a continuous treatment variable, which you could still use a difference in differences on. Okay, so they did this in this case study, I believe. So malaria, it's like a disease spread through mosquitoes. So it kills around 800,000 people per year, most of which are children in Africa. And also, like, if kids have repeated infections of malaria, it will also have negative impacts on their health. Countries with malaria are substantially poorer than other countries, but it's not clear whether malaria is the cause or the fact, right? So is it that having malaria makes you poor, or being poor makes you more likely to have malaria? So that's a really important question. We need to know the direction of causality. Okay, so there's been a lot of organized efforts to eliminate or eradicate malaria. And this provides a nice natural experiment to conduct an impact evaluation. Okay, so first the US in the 1920s, and then many Latin American countries in the 1950s launched major, like really large and successful eradication campaigns. So this is going to look at an eradication campaign in Colombia. So the empirical strategy is as follows. The treatment is considered to be continuous variable, so same as we talked about. In this case, we don't have a DI equals 1 or 0. DI is some variable of treatment intensity. Okay, so areas with higher pre-intervention malaria basically were treated more intensely by the eradication program, right? So places that have super high rates of malaria are obviously going to receive more funding and more treatment efforts compared to places with low pre-intervention malaria levels. Okay, so they argue that basically malaria-free areas should not benefit at all from malaria treatment because they won't receive any treatment for malaria. That wouldn't make sense. So these places that don't have malaria and don't receive treatment are going to be the control group, and they're going to measure the time trend. Okay, so what's this? Exposure to the program during childhood also depends on one's year of birth. Okay, so the program was initiated in 1957. So only children born after 1957 are fully exposed to the program, right? So if the program's launched in 1957, people who were born in 1957 will be treated for their whole childhood, whereas people born earlier might only be treated for part of it or not at all. So the children born at the time of the implementation or after, this implies that these people didn't suffer from malaria in their early childhood, right? Because they lived in areas that received treatment, and therefore they were likely not to miss school because of malaria because they didn't have malaria. Okay. So then they used Colombians born before 1940. So they were adults by the time the eradication program began. So they're the control group because they received no treatment whatsoever because they're too old. There's some kids that will receive partial treatment, some full based on the the year of birth. Okay. I don't know why I put this equation. They did it really weirdly, so I wouldn't recommend. I mean, if you were to do an equation or regression, I would do it like I recommended before. This is just a confusing way to write it. So this is basically what they did, where you have the intensity of treatment, and that's going to be a function of the year you were born. And the, I guess, post would be post 1957, and intensity is determined by how much pre-malaria an area had. Okay. So the only thing I don't like about that example is that they don't show common trends, I'm pretty sure, and it's hard to believe that common trends would be met in that case because you're thinking of comparing places with really high levels of malaria to begin with to places with no malaria to begin with. So they're probably different on a lot of other factors, such as income, maybe education, maybe type of economy, weather, I don't know. So many different factors I think would be different, that would be a hard comparison. But that is a good example for using an intensity variable for a difference in differences. Okay. Any questions? Great. So we talked how important the common trends are. There's different ways to defend them, right? So put your mind as you're an academic economist and you have this beautiful paper using a difference in differences methodology, and you find super large impacts. Well, you need to be able to test your assumptions and show that your results are truly valid. So there's a few different ways to do that with a difference in differences. It's pretty testable. So what? Okay, well, yeah, obviously we talked about the common trends are very important. So without the common trends assumption being true, we would be unable to make causal inference because it is likely the case that the comparison group doesn't act as a suitable counterfactual. So if we have different pre-trends, we won't be able to estimate the counterfactual for the treatment group, right? Because the pre-trends aren't even the same. How can we say that how can we show that the post-trends will be similar? It's just not valid. And remember that the underlying assumptions needed is that selection bias relates only to the fixed individual characteristics. And so those are time invariant, right, or gamma I. And then time trends are the same for the treatment and control group. So that's our lambda t. So if these two assumptions are met, then basically our common trends assumption is satisfied and we have validity. But I mean, we can't really directly test these, so we can't say that selection bias doesn't differ over time. I mean, the time trends are more testable, obviously. So the common trends assumption, one really good way to show it is graphically. So you see here, say this line on top is our treatment group and the line below is our control group. You can see that these are pretty good trend lines. They're very similar before treatment. The only difference is that the post period, right? So we'd feel pretty good about that. So to be able to show your trend line of your outcome variable for multiple periods before treatment, that's a great way to kind of verify that you have common trends. Okay, so that's one method, is graphically like this. And that's just a trend of your outcome variable over time for the treatment group and the control group, right? So you want to split the two groups off. Okay, so obviously if you do that, you might not find always desirable trends, right? So here, it doesn't look super bad, but when you move the lines closer together, you can see that there's clearly just different slopes in the line. It's not that the treatment group had a treatment effect, it's just that the time trends seem to be different, right? So when you have a difference in differences, you really do want to see a change in slope for the treatment group. So here there's really no change in slope at all. It's just two different lines. So that's really concerning. That would not be a good differences. We would probably say there's probably not any true effect. It's just capturing differences between the two groups that are due to other factors like time trends. Okay. So yeah. So besides a really good graph, other ways to do it is a falsification test. So that would be, okay, well, falsification test or placebo dummy. So those are two different strategies that are very similar. And that just shows robustness. And then finally, controlling for time trends directly, which still might not be enough, but it definitely helps if you're concerned about it. Okay, so yeah, this is the first approach, graphically showing that you have good trends. So secondly, we have a falsification test. I'm not sure if you guys have ever heard of what a falsification test is, but it's basically trying to test our assumptions to see if there's a treatment effect when there should not be one. So basically what you do here is you know how you're creating your regression. So you have your three dummy variables, right? You have your dummy variable for the treatment group, you have your dummy variable for the time, and then you have your interaction of your two dummy variables. So you want to now, instead of running your standard regression on Y for the post-treatment period, right? So I'll draw this actually. Okay. Green. Okay. So say, what was I trying to say? Okay. So clearly, so we have our, sorry, I'm scatterbrain right now. So this is our regression. I need to hide myself. So what is it? Beta di, let's say. Plus, call it row times post. Plus, sorry, the, call it delta, I think that's what I called it before. And then the interaction, so di times post, right? So normally, let's say this is t equals 0. This is t equals 1. Let's say we have a period t equals -1. So normally we're running this regression, right? Our yi equals alpha plus beta di plus row post plus the delta, your interaction, right? So di times post t. Normally we're running that on yit for t equals 1. That's our post period, right? So we only expect to see a treatment effect in our post period. If we're doing a falsification test, we can run this regression, but say, instead say for period t equals -1, right? So we would say for this period, if we do this, so in t equals 1, we look at this regression, t equals, sorry, -1. That's our falsification test because we expect to not see any effect size. Falsification test. So when we run this regression on our outcome in period t equals -1, there should be no significant effect, right? Because we don't expect to see a difference in a diff and diff in our pre-period. And that's because our trend lines should be parallel. So if there's a significant difference in the two trend lines, then this falsification test would show up as your coefficient being significant, and that would be a problem because that's if you have a falsification test, you want your effects to be 0 or non-significant to show that your pre-trends are valid. So if you do have a significant effect here, you'd say, okay, well, there's clearly a difference between our treatment trends and our control trends pre-period. So this kind of gives you strength in your pre-trends if you can do this regression on a pre-period and show that it's not significant. That really helps verify that your trends really are similar. Okay. Is there questions on the falsification test? Okay, great. I'm going to delete this drawing. Actually, I'll just leave it there for now. Okay. Oh. Well, this is also, I didn't even mention that way, but this is another way. Okay, so you could also make your basically treatment dummies be in pre-periods. So instead of making our basically saying, okay, well, only for t equals -1, you can leave it the same. So you have your outcome period in the post-treatment. You have it as a function of alpha plus beta di plus rho post t. So it's the same as before. Wait, let's say, okay. But now we can have different treatment dummies that are basically placebo. So that means they're fake, basically. So we have delta di equals post, t equals t equals 3. So that's saying that the treatment happened in period 3. And this one is saying that the treatment happened in period 2, and this one in period 1. Whereas the true policy change occurs at t equals 4. So actually this should be like this. I'm sorry, I make mistakes in my notes, so you guys have to come to class. Kidding, it was an accident. Okay, so y equals, change this to Spanish. Español. So alpha, I'll write that, plus beta I plus rho, I have to write that, post t plus, okay, delta. So this is our true treatment effect. Sorry, this is confusing right now. I'm just making the shell and I'll finish it later. Okay, so t okay. This is our original one, right? So y I t equals alpha, see what I'm doing now, saving time, bi, oh wait, no, maybe not, beta times di plus, call this one rho, post t plus delta di times post t. So that's our standard. But then we can also add placebo dummies. So then we have also delta 1. So that would just be di, same as normal, times post. I'm just going to write that twice. Sorry. but wait. So text draw. So this is di times post. Say t equals -1 plus di times post t equals -2. Okay, so for our placebo test, we expect only to see a significant effect here, right? So this, we want to see stars as in significance. What if we see significant stars in these two? What do you guys think that means? So what if does it mean if we run this equation and find significance in the other placebo dummies? Yes, Susanna, pre-trends are not parallel. That's exactly correct because these dummies, these interaction terms, should not be significant because we should only see a difference in the treatment effect at the time of treatment or after. So if we're seeing a difference before treatment, our pre-trends are not parallel, so we do not have validity. So this is a really good way to check for validity of your model as well. So good answer. So yes, as Susanna said, that means pre-trends not valid when placebo dummies are insignificant, or no, are significant. Okay. Just make sure that you have your original dummy variable for the true treatment effect in here too, so that does make a difference. Do you guys know where the word placebo comes from? I don't think it's the same in Spanish, is it? Oh, it's the same in Spanish. Okay. So yeah, then the name kind of makes sense because it's a placebo. Basically, it's saying we want to see if there's a treatment effect, even though there shouldn't be one. It's like giving someone medicine when there shouldn't be effect, and if you see one, oh, what's going on here? Yeah, the pronunciation. I talk like a very gringa person, so. Okay. Okay, so that's the third way of basically checking your common trends assumption. So if you guys have any questions about any of the assignments or referee report or the slides in general, you can ask me now. If not, I'll let you guys go because we're going to start event studies and there's no time to start it with like 5 minutes left. So we'll just wait till, I guess, the next class. Okay, if not, I'll talk to you guys. I'll send you guys an email actually because I believe your guest lecturer for Wednesday wants to teach live now. So we'll probably be meeting Wednesday at the same time in this meeting room, and I'll just send him the link to it. So you will have a guest lecturer for Wednesday, so that's super exciting. He's going to teach a paper on, I think it was commodity shocks and conflict. So I really haven't talked to you guys about conflict at all. So it's going to be great. Oh. Okay. So I have a question if it'd be possible to postpone the referee report for half a week. That should be fine with me. It's on the 29th, on the Friday. The only thing is, I mean, that's fine with me. Just be aware that you're still going to have an assignment 3 at the end, basically, of the semester. So as long as you guys are making time for both, I'm very happy to push it back if you guys feel like you need it. So yeah, that's fine with me, for sure. So I'll send out an email about that next weekend. Okay, yeah, so I'll look into that then. Okay, have a good evening. Goodbye, everyone. Bye. Stop video. Lecture.